All right, let's get going. So, welcome back. We're into day 20, and is almost upon us. So, this photo's from last fall. Dora down on Hurdles Beach once again, her favorite spot. That I can tell it's from a while ago because there's lots of stands still on the beach now. It's lots of rocks. Anyway, Dora is finally back with me again. I missed her for 2 weeks, so I'll be showing you new photos next time. So what's today? Or at least Tuesday. I'm doing this on Monday. Not a lot I could find. It's National Goof Off Day. Probably not a bad idea. Um, Take it easy. We've got to lighten up a little bit. Bavarian Crepes Day. That those are always good. It's the way I make my pancakes. It's more like a crepe. On campus, I think seasons are over for all of the sports. Teams did reasonably well. That women's basketball team, uh, AUS champs, that unfortunately didn't win the nationals, and the men's hockey team, it did quite well. Um, Lost to UNB, then did get into the finals and lost, I think, to Trois-Rivières. UNB ended up getting the championship in men's hockey, and I think Trois-Rivières was they at least UNB beat them in the quarterfinals. So teams we lost to were uh, high quality teams. Uh, anyway, uh, what is happening though? There's a whole bunch of different counseling services, events, study skills, stress related things that you'll probably see advertised. The two that came to mind, because you're probably focused on just getting through the rest of the term, but you might also be looking at summer employment. And that there are two things going on, and I don't know an awful lot about either one, but they uh, you should be always be thinking about employment. That you don't leave it until too late. And there are lots of opportunities. You may have a nice, safe job that you've had before you can go back to, but it's also helpful to have diversity in your work experience. So looking into other avenues is always attractive. So with the last few classes coming up on us, uh, encouraging you to check up grades on Gradebook. I think I've been checking them up. Last night, I was contacting lots of people about test four, um, but I'm seeing lots of students with little bits missing. And if you're missing an assignment or a test, that's a big ticket item. It's just killed your grade. Still pass, but you're not going to do nearly as well. That if you're missing something, talk to me about it. Course evaluations, the university ones, come out next week. They're on Brightspace. You'll be seeing them with all your classes. I would ask that you do it for this course as well. I'm sort of more concerned with the other instructors teaching in the course, but you're taking it from me. So anyway, um, related to that though, some of you have responded to the course feedback survey that I launched last week. I'll be sending out a reminder tomorrow, and I'll keep sending out reminders on it. It's the survey that's important to us because it helps us redesign the course or make continuous improvements to it. That so much of the way this course is delivered has been on the guidance of the students taking it. They've given us lots of feedback and we've followed up on it. You have an assignment that's due this week, and that by the time you see this, I'll probably have posted the tutorial that I'm doing later today. Um, but our last test is next week, so we're almost at the end. There'll be just one more assignment, and I'll try to keep it short. So let's get going. Last class, I did decision trees. I'm not sure how well I did a job on that. It's actually a simple concept, but it's hard to work through an example because it's so tedious that decision trees go and take a large group and that may be hard to make predictions about and split it into smaller groups where it might be easier to deal with the small groups. And if it isn't great with that small group, break it up into a smaller group. Keep finding smaller groups where the we get down to ones that it's easier to make predictions on these little small groups that where everybody looks alike. It's really quite straightforward though, and it's just by this partitioning process. So we look at different variables we could use to do the partitioning on and try to figure out, is a split, are we better off looking at two small groups than one large one? And the two small groups being ones that are more predictable. And that this process of doing it starts to look like a tree. That the challenge at times is trying to figure out, well, you've got lots and lots of variables to split people up on. Which ones should you pick? And there are different guidances for doing that, different measures of how much better you will be by splitting. And with this particular variable, they're all sort of similar. There isn't a, the numbers look different, but in the end, and one of them may split on variable A and another one on variable B, but you're going to keep splitting over and over again. End result may not be that different. At least in performance. The trees may look different, but they perform similarly. That when we're splitting them, we're trying to get nodes, groups, that are, in a sense, cleaner, that everybody in the group or most people in the group with insurance would renew their insurance, or everybody, most people in that group don't renew their insurance. So that if almost everybody's the same, it's easy to predict what's the behavior of people that would typically be in that group. Okay? And that comes out by looking at scores. We looked at Gini scores. Gini scores go from 0 to 0.5. 0 is a really clean group. Everybody's the same. 0.5 is like 50-50. 50% are yes and 50% are no. It's really hard to make any predictions. We say it's dirty. And we go through trying to pick, if I've got a choice of several variables to pick from to do the split on, I'm greedy. I pick the one that seems to have the lowest Gini score. Gives me the best return. I'll split on that one. And so we had this sort of tree that we had previously, and it starts out with a Gini that's close to 0.5. It's 0.48 because it's almost 50-50, 60-40 split that we've got here. My picture's flickering again. Yep, let's leave that for now. And if I split it male-female, the male group is just as bad as what I started with. But the female group is much better. It's a 0.32, so it's a good split. I should go and use that one. And then if I split the male group by age, so below 50 and above 50, it's both splits are better. I get 0.28, 0.38. It's a good idea. If I split females by marital status, married ones are much better. The Gini score is getting closer to 0. For single, it's much worse. In that instance, we have to take a weighted average of the two to see if on average it's better than a 0.32. I don't have that shown in my chart here, but I think I showed it to you last time when I was looking at trying to predict or identify who is satisfied with their experience at St. Mary's and who is not satisfied. So, but this type of process that you're going through, in the end, you end up with some groups like these last ones where we have males over 50 that had an accident. They don't renew their insurance. So my rule would be, if the customer is male over 50, has had an accident, they're not going to renew. That's my prediction. If they're male over 50, they've had an accident, they will renew. That's my prediction. If it's a female that's married, I think she's going to renew. That I'm trying to get down to ones where it's almost perfect. You know, the Gini score is super low. And with those ones, I've got a really simple rule to be able to describe that. Generally, these rules work very, very well, but they require an awful lot of data. Like with the student data, I still haven't gotten back to working with it, trying to make better predictions. But I started out with 1,000 observations. Survey data we had was a little bit more than that, but I had to throw out some data. But it doesn't take me long before I split and get down to little groups of maybe 40 or 50 or 60. So to build a really complicated model in predicting who's dissatisfied with their experience at St. Mary's, I probably need 10,000 or 100,000 observations. I won't get that in 4 years. It's taken me 4 years to get 1,000 observations. Um, that sometimes, as I said, you can get to very small subgroups. That's not a good idea. You need to keep those subgroups reasonably large so that making predictions based upon that group, you're making a prediction based upon a group of 50. Okay, it's a reasonable amount of data. Making a prediction based upon what happened with a group of 4 people, that's iffy. You've only got 4 that look like that. Uh, it may be suspect. That if you allow those subgroups to get too small, you end up getting into a problem we call overfitting. You fit your model so perfectly to the data, it works with your training data set beautifully. But then when you apply it to new data, it doesn't. So it's a little bit different. What do I mean by that overfitting? I know this doesn't fit with our data set here, but think back to regression when we did it before. So here are the blue dots that you see there. And when we were doing value estimation, we would have put the orange line through it. And it's the best relationship between output, the number of units we make, and what the total cost is. So we've got this historical data making different batches of 2,000 units, 4,000, 6,000, so on. And what was our total cost for each of those batches? And so we got this chart here. And so we'd put a straight line through that so that we'd have the slope being our variable cost. What's the cost for an additional unit? And the intercept would be our setup cost. Oh, that makes sense. But if you use that model to make predictions, you would find that of the 10 batches I've made before, almost all my predictions were incorrect. A little bit too high, a little bit too low. If you wanted to make much better predictions, then you could have built a different model. Instead of putting one simple line through it, the orange line, I could have connected the dots and have the model described by the blue line. Okay. So if someone came along and said, okay, make me a batch of 2,000 units, how much is it going to cost? And you say, oh, it's going to cost you $13,000 because that's what my blue line says. Oh, okay. Well, what if I asked you to make 3,000 units? Oh, we can do that for $11,000. Hello? That doesn't make sense. If I want 2,000, it'll cost me $13,000. But if I want 3,000, it'll cost me 11,000. So obviously, I'm going to ask you to make me 3,000 units. It's much cheaper. I'll just throw away the ones I don't want. That doesn't make sense. Those are stupid predictions. I'm not going to, the next batch I make of 3,000 units is probably going to cost more than $11,000. That was just a batch that, for whatever reason, I was more efficient making. Okay? And similarly, the one before that, where it cost 13,000, that one might have been a bit above average. So the next batch of 2,000 might cost me 12,000 or 12,500. These are, I'm reacting to the noise by putting in the loop line. We call that overfitting. You're just following the noise. You're not following what the real relationship is between these variables. And so we've got to watch out for that. And decision trees are a case where we often make that type of mistake, but it isn't quite as obvious as you're seeing here with this regression example. So, but despite this issue about overfitting, decision trees can be really appealing. They're There's no real theory to it. They're very simple. It's very pragmatic. It's logical. People see it. Hey, it seems to make sense. It fits what we've seen, and they're easy to implement. It doesn't really tell you why people renew their insurance. Okay? That it just this seems to be the pattern in the data. So it may not be great for causal modeling because each group might be very, very different. I can't establish big, broad, overlying relationships that are here. It's great if you just want a prediction. Now, before I leave this, I do want to mention one other thing. There are times when, when you're trying to make a decision and you ask your friend and they say, well, I'd do something different. And you ask someone else that you think whose opinion you trust and they suggest something else again, that the different people will come to different conclusions because they make slightly different assumptions, not because, right and wrong and all that sort of thing. And but if most of your friends said the same thing, you might go along with that then. So it's a consensus type decision. What would happen if we did that with decision trees? That suppose we had 10 data analysts, and instead of taking our big data set of 2 million observations, we gave each of them 500,000 observations. It's a lot, 500,000 each, and they were different samples you took. So they got 10 different random samples. So it's really big, enough for them to build a practical tree. But there are differences in the samples. So the trees are going to be slightly different for each of these ones. And that they'll probably be equally good because they've used so much data. But the trees look different. Okay. That you would probably find, though, with most cases, most of the trees come to the same conclusion. But let's build a rule then. We create 10 trees, and then we look at what the average is or the majority of the trees say. So for each prediction we make, it's going to be based upon a consensus of sorts among the forecasts that we've got. Sound interesting? It's actually a very popular technique that it's called a random forest. So if you take a whole bunch of trees and put them together, we call it a forest. And these trees were created by randomly picking different subsets of my data to build the tree. I found it a very strange name. It took me a while to figure out what is this thing, a random forest? I thought it was a totally different approach. It's hard to explain, again, my predictions for single case. It's that I built 10 models and this was the consensus of those models. So again, it may be difficult to explain to someone, but it works very, very well. Okay? That this idea of combining forecasts to make a consensus forecast is a route that's become very, very popular in the last decade or more. That these consensus methods, they call them ensemble methods, an ensemble collection. But suppose we want a method that also does causal analysis, like we had with regression, sort of. Well, here we get messy. So hopefully you'll follow some of this. So this is a method called naive Bayes. It's based upon Bayes' rule. We want to make a prediction of an outcome given customer information. Okay? And we'd like a probability that's very close to 1, very close to 0. If our prediction has a probability of 0.9 that you're going to say yes, then we'd say, yeah, they're probably going to say yeah. And if the probability is like 0.05 that you're going to say yes, then we're going to say no, you're going to say no, you're not going to renew your insurance. So that if we can get those probabilities to the extremes, then that would be attractive. Closer we can push them to 1 or to 0, better it is. So can we come up with a method that may not be great at estimating the probability exactly, but helps push our estimate in the right direction towards 1 or pushes it towards 0. So we're not looking for an ideal prediction here. Now, we're looking at the insurance case, we've got lots and lots of our customers that renewed. So let's look at all those that renewed and look at the information we have about them. And then we've got another bunch of customers that didn't renew. So let's look at them and look at the information we have about them. And we try to use that to build models. It's sort of what we've been doing before. What we want to do now is flip that probability around. So given what we know about the customer, what's our prediction? So that idea of flipping is what Bayes' rule is all about. So let's go back and look at Bayes' rule. Bayes' rule said probability of A given B is the flip, B given A. That's probability of A divided by probability of B. Don't worry about understanding why those three terms are organized the way they are. Just think of the different things we need. So in the insurance example, we want to predict whether or not they're going to renew their insurance, and B is everything we know about them. So for a male over 50 with no accidents, we want to predict, are they going to renew? Now, forget the tree that we've already done. So by the rule, let's put the things in. We would have probability male over 50 with no accidents given that you renew. So look at all the customers that renew. How many of them are male over 50 with no accidents? Or what proportion of those that renew? The next one, it says probability renew. So I look at, okay, what proportion of all my customers renew their insurance? I think that was 60% we had before. Okay. And then what proportion are male over 50 with no accidents? So we've got this little group of customers. What percentage of my total customer base does that represent? So on the top, I've got the proportion out of those that renew. On the bottom of my fraction, it's just out of all customers. Okay. So this is the description I just gave you. I've gone through and I've looked at my data and tried to find all of these different sorts of things that if I got a lot of data, I can probably find all of this stuff. Okay. But if you think about it, suppose you've got 10 different characteristics on customers. And for each of them, you have 2 categories. So even on age, I'm just doing over 50, under 50. If you want to look at other age groups, then that's really like more variables I got to throw in. But just with 10, it means I've split everybody up into 1,000 groups. That's a lot. So if I've got 50,000 observations, then I've got an average group size of 50. If that's the average, it means I've got probably a lot of groups that are really small. I may even have some groups where I have nobody fitting the group. Some groups can be super tiny. That's a real problem. This method is just as bad as decision trees. I run out of data when I keep splitting like this. So this bit of theories may not be able to help me. Okay. And these variables I've got, they're all interrelated to each other. Just like in regression, we had correlations happening. That accident rates for people over 50 and under 50, you think they're going to be the same? What about males under 50 and females over 50? Well, they might be a little bit more different from each other. Each of these customer characteristics is probably not independent of others. There's interactions among them. So understanding there's an interaction between accident rates and age and gender, number of years driving, previous accident record, type of car they might be driving, a whole bunch of these things. So the issue of multicollinearity we had in regression, we've still got here. So that complicates things as well for us. But what if we were stupid? We're naive, we're simple-minded, and we're going to totally ignore the fact that these different variables might be interrelated. Let's make a big assumption that they're independent of each other, that a 90-year-old driver and a 40-year-old driver have the same accident rates. They have the same behavior. That uh, I don't think that's true, but they let's presume that's the truth, that they're all independent of each other. Now, our goal here isn't necessarily to estimate probabilities precisely. Sort of think like linear regression, where we knew it was a model that gave some stupid probabilities, some that were less than zero, some that were greater than one. But did it point us in the right direction? Did it help us identify those that were likely to renew versus those that were very unlikely to renew? And just point us. Which way should we be thinking? That we want to find a relationship that will help get us a probability that is it closer to zero or is it closer to one? Okay. Now, if they're independent, I've described sort of what I mean by independence in words, but from a probability perspective, that the stuff we did a week ago, the probability of A given B, so the probability you're going to have an accident given you're over 90 years old is the same as the probability you're going to have an accident. Age has no bearing on it. So that may be questionable. The chance you're going to have an accident um, given your eyes are blue versus what's the chance of having an accident given your eyes are brown? Probably the same. Knowing eye color and accident rates are independent of each other. That we're going to assume all of our variables are not interrelated in that fashion. So it really simplifies things. The probability of A and B happening is probability of A times the probability of B. The probability of being a male over 50 with no accidents is the probability of male times the probability of over 50 times the probability of no accidents. Okay? If they're all independent. Yeah, okay. Why? Well, um, why might it be helpful to me? If I take that big formula I had, it means each time I get these ands, this and this and this and this, I can break it up into things that are multiplied together. And even conditional probabilities, male over 50 and no accidents given renew, I can split it up as male given renew times probability over 50 given renew times probability no accidents given renew. So I split it up, multiplied them together. I've rearranged things so it becomes a bunch of little pieces that um, will just multiply together, a series of ratios. What's attractive about this is look at the probabilities I have to find. Before finding out how many males over 50 with no accidents did I have out of all my customers, that number that's at the denominator, at the bottom of my big formula here. And if I was looking at a group that was really, really small, suppose it was male over 90 that had several accidents or I don't know, something that, and I had many more variables, I might find I've got a group with nobody in it. That would be a problem. But in my new formula, I'm looking at, well, what proportion of my customers are male? What proportion are over 50? What proportion have no accidents? Those are ones that are very common things. Those are easy to estimate. What about males that renew? Well, out of all my customers that renew, I'll have some males, I'll have some over 50, I'll have some with no accidents. So again, these probabilities are easy to find. And the estimate should be reasonably accurate of each of these because I've got lots of data, I would hope, on each variable that I'm looking at. This is easier to calculate. Okay? That If I look at the different terms in this, like the very first one is probability male given renew divided by probability of male. That, what's that ratio? Well, suppose that um, half of my customers are male. So that's 50%. The bottom of my fraction here is 50%. But among those that renew, they make up only a third of my customers. So just looking at those that renew, there aren't as many males in that group as there are in the whole population, or proportionately. The ratio is 0.67. So this ratio that I've got, it's less than 1. So if you look back to the formula, I've got something times something times something times something. If you multiply a term by a number less than 1, it makes the whole thing smaller. If you multiply by something bigger than 1, it makes it bigger. It's like inflation. If inflation is bigger than 0, it's like multiplying by 1 point something, and the new price is going to be bigger. That deflation, it's inflation is negative, it makes you'd be multiplying by a number that makes it smaller, like having a discount makes it smaller. And the, whoops, wrong way. So if the customer is male, that tells me it's less likely they're going to renew. That when I was looking at trying to predict whether or not you were unhappy with your experience last fall, I started looking at variables where with these ratios, which ones were bigger than 1 and which ones were smaller than 1. Okay? And that I was finding that students that had low grade point averages, this ratio was less than 1. Students that chose St. Mary's for some reason other than the program, chose it because of location or cost, or their friends were going here, they had a ratio less than 1. If I looked at students that said they had been depressed frequently, then their ratio was less than 1. So I'm starting to get an idea that, okay, if you're this and this and this, each of those things is going to have some impact and reduce the probability. So someone with lower grades didn't come here because of the program and has been experiencing depression, you're much more likely to say you were unhappy or much less likely to say you were happy with your experience last fall. That so when I get combinations, that's going to be useful to me. And those ratios, we call them lift. And so if the lift is greater than 1, it increases likelihood of something happening. And if the ratio is less than 1, it decreases the likelihood of something happening. Sort of like if the correlation was positive or negative. A lift that's bigger than 1, think of like a correlation that's positive. And a lift that's less than 1, think of it like a correlation that's negative. And these are nice. Give me an idea of what are the drivers of people being happy or unhappy. And that if I've got enough of these ones, it's me drive those probabilities down closer to 0 or closer to 1. There'll still be some that it sits in the middle. But these ratios can be helpful to us in identifying factors that we may be able to influence to improve um, probabilities, improve the results that we want to get. The method is known as naive Bayes because we're making this simple-minded choice of this assumption of independence. It actually works very, very well as a classifier. It's not the greatest in estimating the probability. So, but then it's just we're trying to get if the value is very, very close to 0, then we're saying no. And if it's very close to 1, we're saying yes. But is it pointing us in the right direction? And it seems to do that quite well. The idea of lift is often very attractive because you're predicting this customer is unlikely to renew their insurance. Oh, what can we do about it? Are there some of those ones with Lyft that we could use to change what happened, change their behavior, and move it more in terms of our favor? If I was looking at improving student satisfaction, knowing who are the ones that are likely to be less satisfied with their experience, it gives me students to target and potentially not just target them, but know, okay, this may be part of the reason why. Is there an intervention I can do with that student to address that issue, change their behavior? But you've got to be cautious because these variables aren't independent of each other. Okay? So just to give a quick summary, that we've looked at quite a few, that they're all quite different from each other, and there are lots and lots of other ones out there, but there's no one that stands out as being the best. That part of the reason why am I introducing so many methods in a lot of courses, like if you took Quant 1, that in the finance section, how do you work out loan payments? There's only one answer to it. Really simple. That if it's this problem, you do this. There's a specific tool to fit every problem. In practice, that's not true. That we rarely have problems so well defined that we can always pick a best practice. That they don't exist. We have choices along the way. And the choices, even when we were building a regression model, we made choices of what variables to include. And so different individuals can reach different conclusions based upon slightly different assumptions or choices that they've made along the way. These models themselves are abstractions of the real problem. They're not perfect. Okay? So again, don't get obsessed with a specific tool. Classification encourages us to look at it in many different ways. And this idea of ensemble methods, why I mentioned random forest, maybe the best route is to use several models and combine them in some fashion. So get different opinions. And, but it may be just different problems, approach them different ways. Okay? So if I've got multiple ways to do it, I've still got to end up deciding which one do I go with? How do I decide what is good? What is best performance? And best is not easy to define. That you will hear in many courses, oh, our best practice. Best practice means you need a very clear objective. And if you did Quant 1, you did optimization. So you maximize profit. So this is the choice to maximize profit. Even if it destroys the environment, it'll give you the maximum profit. Oh, no, I don't want to destroy the environment. I want to, oh, okay, that gets more complicated. Then you don't have one objective. You may have several. There may not be a best solution for you then, because it depends upon how you're going to balance profits and the environment between the two. But we'll look more at how do you make those trade-offs, those evaluations. And there isn't, again, a right answer there. It'll depend upon the context. Anyway, we're done. So thank you. Bye.